We are now going to look at a very, very important concept. Okay, so this is the idea of velocity of approach and velocity of separation. So let us think about a point which is fixed. Let me say that it was O, and let us look at an object. Let us call this x. So x has a velocity like that. Okay, OX is the distance, initial distance between O and x. Now, if this is the velocity of x, so let's call this v. Now the question is the velocity going to reduce the distance OX? Is it going to increase the distance, or is it going to remain the same? What do you think? Well, if I showed it to you like this, clearly x is going to go to this place after a little time. So once you go here, you can see that the distance has decreased. Okay, but can I use this idea and say v into t is this displacement? That is true, right? So this is v into t. But is vt the reduction in the distance? OX and OX dash, OX minus OX dash, is it equal to vt? What do you think? Is this correct? No, this is not true. Why is this not true? Why is this not true? Because you see, for example, if v was perpendicular, let us start with a very simple case. Let us say that the velocity was perpendicular. Then you know that it is going to go in a circular path. If it is always perpendicular, it will be in circular path. At least from here to there, you know that OX and OX dash, not much of a change. Okay, you know that if the velocity is perpendicular, that means it's trying to go in a circular path. Of course, it won't go in a circular path if it continues to be the same direction. It should always be perpendicular. If it is always perpendicular, it will be a circular path. But if it's a circular path, what does it mean about OX? OX hasn't changed. So if it was perpendicular, then the line, the vector OX will turn, but it will not become shorter. Okay. On the other hand, if v was like this, then a little later, this is where x dash is. So OX has definitely come down. In that case, you can say it was vt. But in general, if it looks like this, let us say this angle is theta, you should take the component of v in this direction, which is v cos theta. Then there is a component in this direction, which is v sin theta. It is the v cos theta which is reducing the distance. So OX minus OX dash is v cos theta into t. Okay? So far it has nothing to do with relative motion. Basically, the velocity of approach is, if once you think of this fixed point, how much closer are you getting? Okay, you may be going also turning around. Like for example, because of this velocity, you are going to not reach O directly. You are going to go like this, right? You are going to go in a curve. You are not reaching it like this. You are going around like that. But this component is only making you turn. This component is the one that is getting you closer. So what is making you approach O? V cos theta. So we call V cos theta velocity of approach. It is not the same as the velocity of the object. It is not relative velocity. Relative to O, what is the velocity of x? It is v. It has both v cos theta and v sin theta. But what makes you get closer? V cos theta. What does v sin theta do? It just takes you around. Okay. Now instead of the velocity being like this, so suppose this was O and this is x as before. But now let's say if I had a velocity in this direction. Okay. So let's say this was v. Now what is going to happen is you are going to have a v cos theta like this, and you are going to have a v sin theta like that. Now because of v cos theta, what is going to happen to this point x? It's going to go further away. Okay, but how much further? The basic idea here is that we don't care whether you are here or there. We only care whether you are further away or closer. That means if you have turned, no problem, just simply turn your whole up. Like look at this and you look at that. You say, okay, this is OX. Let me draw an arc. So that is OX dash. How much is the extra? OX double dash, let's say, or this is also like OX. X dash, how much is this extra? That's basically what we are interested in looking at. Okay, we want to look at that distance. Who contributes to that distance? V cos theta. Okay, so v cos theta will be velocity of approach if it is moving towards O. It will be called velocity of separation if it is moving away from O. So is x approaching O or separating is not determined by the entire velocity of the object. It is decided by the velocity towards O or velocity away from O. Only this part. So we call this velocity of approach or separation. Turns out to be very, very useful in many questions. Like for example, so you have an object O, okay, I mean a fixed point O, and you have an object, let us say at a distance of 20 meters. It is always moving. It is always moving such that, so this object is x, okay, it is always moving with a constant speed of, let us say, 10 meters per second. But it makes an angle of 60 degrees with the line OX. So what does that mean? Right now it is making an angle 60 degrees. It's not constant velocity. When you come to this point, this is OX. Now what should be my velocity direction? It should again be 60 degrees, but it should be 60 degrees with the new line joining. So this must be the new velocity. It is again same speed 10 meters per second, but it's always 60 degrees. So what will be the path of this object? This is going to not move like this, actually it's going to move like this. It is going to spiral and it's going to come and meet that point O. It is going to spiral and come and meet that point O. Now the question is, how much time does it take? Well, let's think at any instant its velocity is 10 meters per second, but the velocity of approach, what is the velocity of approach? 10 cos 60. So 10 into half. It is 5 meters per second. That is, it is getting closer at the rate of 5 meters every second. How much closer should it get to meet? 20 meters. So time must be 20 meters by the velocity of approach 5 meters per second. So it is 4 seconds. So in 4 seconds it's going to strike. But just imagine this path. If you look at the path, it's a very complicated path, right? It is turning all the way around and reaching it like that. So the velocity of approach helps you quickly calculate how soon it will reach there. But if you try to calculate the path, it's going to be much more messy. So I hope the idea is clear, because at constant velocity of approach, the velocity of approach hasn't changed. Why? Because even though I have gone here, it is still making an angle of 60 degrees. When I go here, then it makes an angle of 60 degrees with the new line and so on. So that means the velocity of approach is always going to be 10 cos 60. That's all matters. So that means it's always 5. So it's constant velocity of approach. Okay. On the other hand, if this guy was moving with a constant velocity, will it reach this place? No, because here it may be 60, but once it has reached there, this angle is not 60. This angle is more. Then there is a point where it becomes perpendicular. After that, it's going to actually start separating because it has a velocity of separation. So velocity of approach gives you very quickly a way to calculate answers for certain questions. So this is one of those examples. Now what to do if both O and X were moving? Right now we were assuming O is at rest. But if O was not at rest, let's say O was also moving, X is also moving, then what do you do? What will we do? We'll use the idea of relative motion, because this is such a powerful idea that if you make one of them at rest, then you can use the idea of velocity of approach. But how do I make one of them at rest if both were moving? Use relative motion. So relative to O, let us calculate the quantity. So let us take an example and try this out. So now let us look at this case where A is moving horizontally. I am going to say that it has a velocity of 4 I cap. And let us say that B is somewhere here, right below. And let's say the distance between them is 20 meters. And B has a velocity like this. Okay. And let us say the velocity's value, the size, the velocity of B. Let's come up with some number. Let us say it is 3 I cap plus 7 j cap. Okay. Or let me make this 8 j cap meters per second. Okay. So that is the velocity of B, this is the velocity of A. Now the question we want to know is, how much does the distance AB reduce? What is the rate? Rate of change or rate of decrease in this case of the distance AB. How much would this be? Well, that is actually the same as the relative velocity of approach. Okay, so what we can do is first let's say we make A at rest. How do we make A at rest? You add a minus VA, which is minus 4i, then this will cancel out, so A's velocity becomes 0. And you have to add a minus 4i like this, right? If I add a minus 4i cap, B's velocity becomes something like this. So A says B is going like this. You will be saying B is going this way. But A is going 4i, so it's going horizontally more than B is going. So if A reaches here, B is a little bit behind. It is going up, but it is behind, right? So relative to A, what will happen? B is actually moving in this direction. How much is this velocity of B relative to A? How much is that? It is velocity of B minus velocity of A, which is what I am calculating. This plus that, this minus A, right? So if I did that, I am going to get minus I cap plus 8j cap. Okay. Now the question is, this is the velocity of B relative to A, so it's basically moving like this. But what is the rate at which it is approaching A? Not this velocity. You must take the component along A. But what is the component along A? The j cap component, which is actually 8j. So this is 8 meters per second. Because this is the velocity of approach of B towards A. This is the rate at which B is approaching A. Because what matters is the velocity along the line AB. Now A itself doesn't have a velocity along line AB because it had a perpendicular component. If A's velocity was like that, then when you did the relative motion, A is going to be at rest. You may end up with B's velocity being something. Its component along the line AB is the relative velocity of approach. So I hope the idea is clear behind this, how to calculate. Now let us see, that is the rate at which it is decreasing, the distance is decreasing now. But as it keeps going, here you must take this component and that won't be 8. When you are here, you must take this component, that also won't be 8. So this 8 is only at this instant. Okay, it is not that it is going to be always 8. So you cannot say distance was 20, relative velocity of approach is 8. So they are going to meet after, well, this is, if I divide by 4, this is going to be 2, that is going to be 5. They will meet after 2.5 seconds is clearly wrong. Because they won't meet. Look at this, B is going away like this. So they will not meet. Why? Because this is 8 meters per second at this instant. It is an instantaneous velocity of approach. Okay? Because the component you are taking, this is constant velocity. It has a constant velocity, relative velocity of minus I cap plus 8j cap, but its velocity of approach keeps changing as you go from point to point. So now let us take this example where I have A moving with a velocity of 4i cap. And let us say B here is moving in this direction with a velocity of, let us say, 3i cap plus 8j cap, like we had earlier. Okay, but this time I don't want to know what is the velocity with which B is approaching A. I want to know the closest distance between A and B. The point is, if you try to do it in this diagram directly, it's going to be very hard because you see A is going to move here, B is going to move there. Clearly this distance is closer, but after some time A is going to be there, B is going to be here. You need to find that distance. Is this the closest? I don't know, because as you keep going, after some time what is going to happen is B is going to go there, A is going to be here, the distance will increase. So there is a closest distance, but it's not easy to see from here. To understand how to do this type of a question, the best thing is to make everything relative to A. So A's velocity becomes 0. A is not moving. So at least one thing you fix. How do I do that? Add a 4i cap, and if we did that, then B's velocity, relative to A, okay, is going to become 3i plus 8j minus 4i. So it's going to become minus I plus 8j. So that means B according to A, now A itself is moving but we don't care. Right now we are going to say A is fixed. So this is 20 meters. Let's say that was the starting point. And A says B is moving along this line. So if B is moving along this line, when will it reach the closest distance? Is it here? Well, this is less than 20, but that is not the closest, because if you go a little further, again it will be even lesser. So when will it be the closest? When you have this perpendicular distance. So this is going to be the closest distance, AB dash. If you go further away, the distance is going to become larger. So what we want is D. So if you want the closest distance, and many times you'll be asked that type of a question, closest distance, the best thing to do is to make one of the objects at rest. So relative to that, you look at the other object, because then it's simple. A is at rest and B is moving. It's very easy to realize, at least geometrically, that this is the closest distance. But how do I find out the closest distance? Well, I've got this, I've got that is 20, but you've got this velocity is minus I plus 8j, which means this is minus 1 and this is 8. Or this is 8 and this is 1. So tan of theta, okay, look at this angle. I have not called this as theta, I am calling that as theta. Tan of theta is, so this, this distance wise it's only 1, it's not minus 1. Okay, minus 1 tells you that's in this direction. 8 like this, 1 like this. What is tan of theta? 1 by 8. Okay, but tan of theta must be equal to d by this. It must be equal to d by bb dash, which I don't know. What I would have been happier with is sine of theta, because if I knew sine of theta has to be d by 20. But if you knew tan theta is 1 by 8, this is 1, this is 8, what is this? Root of 64 plus 1, 65. So what is sine theta? 1 by root 65. But do we know sine theta for this triangle? It's an right angle triangle. Sine theta will be d divided by the hypotenuse 20. So d by 20. So what is the value of d? 20 by root 65. 20 by root 65. Correct? So this tells us how quickly we can calculate the shortest distance between A and B in a problem like this, where this guy is going in some path and this is going in some other velocity. What we do is, relative to A, we calculate the relative velocity of B, relative to A. Do the whole problem with respect to A. And then the problem becomes a lot simpler because it's just a straight line. What is the closest distance? The perpendicular distance. Okay, if both were moving, then you can't do that so easily. So always transform a problem with two objects moving to one of them watching the other. A lot of concepts get a lot more simpler. So I hope the idea is clear. So we have now seen what is the use or how to basically calculate velocity of approach, velocity of separation, as well as how to calculate the closest distance. The best way to, as always in physics, to learn something is to apply it to a whole bunch of problems. So please try them out and then look at the solution videos.